Okay, this is part 2 of section 8.5. We left off with graphing this one. Let's take a look. E. We've talked about E before. E is an irrational number, just like pi is. E is approximately 2.718. But in one sense, it doesn't really matter, because if I'm graphing it, it doesn't matter what that number is, as long as it's not a fraction, which 2.718 is not less than 1. I'm still going to go through the point 0, 1. It's still going to get close to my horizontal asymptote. It's still going to go up and to the right. Doesn't matter that we call it E. It's still going to look the same. And my horizontal asymptote is still going to be y equals 0. I'm going to have you try this one on your own. This is the same graph. You're just going to shift it. Let's take a look at this one. Notice this time I do have a fraction, so it is going to change how the graph looks slightly. If we plug in these x values, again, 1/2 to the -3, if I have a negative exponent, that is going to flip this fraction upside down, y equals 2/1 to the +3, which is y equals 2 to the 3rd, which is 8. So if I plug in x equals -3, I get 8. In the same way, if I plug in -2, I get 4, 2, anything to the 0 power is 1. If I plug in 1, I have 1/2 to the 1st power, which is 1/2. If I plug in 2, that's 1/2 squared, or 1/2 times 1/2. Remember, when you multiply fractions, you multiply the tops, you multiply the bottoms. 1 times 1 is 1, and 2 times 2 is 4. 1/2 to the 3rd power is going to be 1/8. So these numbers should look familiar to you. We actually plotted these points, or at least similar points, before. So if I have -3, 1, 2, 3, 3, 4, 5, 6, 7, 8. Remember, in the last time we did +3, 8. This time we're doing -3, 8. -2, 4, which will be right about here. -1, 2. There's that 0, 1 again. And 1, 2, 3. I get closer and closer and closer to the x-axis, but I do not cross it. So I have a horizontal asymptote again at y equals 0. So the shape should look familiar to you. The only difference is, instead of going up and to the right, now we're coming up from the left and going down towards the x-axis. I'm going to have you do this one on your own. All we're doing is shifting it. So instead of going through that point, we have to shift it. Remember, +2, it's going to go left 2. So we're going through this point right here. And I'll have you finish this one on your own. 1/7 to the x plus 1. This is also going to get shifted. So instead of going here, it's going to shift it up 1. Okay. Finish this one on your own as well. All right, let's look at example 13. You notice it has an asymptote. We're getting closer and closer to the x-axis. So we can rule out these two automatically. Well, there's actually another reason why we can rule those out. But the biggest reason is the +6. +6 would indicate we would have moved it up 6 units. We didn't really do that. The other reason why we can cancel or cross those out is because this says x squared. X squared, if you recall, the x squared graph is a parabola, which is not what we have here. Okay, so we know it can't be A or C. So now we have an exponential function here and here. Notice they're very similar. I have 2 raised to the x plus 1. I have 2 raised to the x plus 1. The only difference is this number out here. And here is how you're going to be able to tell which answer is the correct one. If I have 2 to the x plus 1, what I'm going to do is I'm going to plug in x equals 0. If I have 2 to the 0 plus 1, that is 2 to the 1, which is 2. If I plug in 0, I'm going to have the point where the x is equal to 0 and my y is equal to 2. So if I look at my graph, I should have a point at 0, 2. And if you look at that graph, you notice that the graph does not go through the point 0, 2. So you can cross out that one. We've already crossed out these two. The only possibility then is this one. Exponential growth models, this is the formula. Okay. When a real-life quantity increases by a fixed percent each year, the amount can be modeled by the following equation. What I'm going to be asking you to do is to write the model. In other words, I'm going to ask you to write this equation right here, filling in A and R. A is the initial amount, what you start with. R is the percent increase, and T is time. Percent decrease is a very similar formula, but instead of 1 plus R, we're going to do 1 minus R. Other than that, everything is exactly the same. In 1990, whenever they give you a year like that, you don't need to worry about it. The cost of tuition at a state university was $4,300. This tells you the initial amount. And by the way, just because this problem has words doesn't mean you get to skip it. Read the words. It's an easy question to do. During the next 8 years, the time doesn't matter. The tuition rose. In other words, it increased 4% each year. Write a model giving the cost. Well, if we're rising, if we're increasing, that was this equation right here. And I told you you needed to give me the A and you need to give me the R. So A is the initial amount, what we started with. Well, we started with 4,300. And it rose by 4%. Now, this is 4%, but I need it as a decimal. If you recall, converting percent to a decimal, you're going to move the decimal 2 places to the left. So 1, 2. Well, there's not another number, so here's my decimal, which means I have to put in that 0. So 0.04 raised to the t power. I will ask you to actually add these numbers together. So if I have 1, and I want to add 0.04, remember when you add decimals, you're going to line up the decimals. Well, 1 doesn't have a decimal, so I'm going to put 1 in. Okay. And also, I can add zeros, and it won't change anything. So I'm going to write that as 1.00, and I'm going to add 0.04. If I add this, I've got 4. I add this, I get 0. Drop the decimal place, 1. So my final answer, y is equal to 4,300. 1.04 raised to the t, and that is your answer. Buy a new car for $24,000. Each year the value of the I'm not sure whether it's a car or a coin. Decreases by 16%. Write a model giving the value of the car. Well, apparently it's a car. So, decrease, that's going down. So it's 1 minus r to the t. We know the initial amount, that's 24,000. 1 minus what it decreases by, the rate, which is 16% or 0.16. raised to the t. Again, I'm going to ask you to combine the 1 and the 0.16. I need you to subtract those. 0.16, and I want you to subtract. This time I'm going to have to borrow. So I'm going to take 1 away from the 1. I got 0 left. I've got 10, but I got to borrow from that, so I have 9 and 10. 10 subtract 6 is 4. 9 subtract 1 is 8. And I bring down the decimal. Final answer, y equals 24,000.084 raised to the t. I'm going to have you do this one on your own, and this one. Let's take a look at this. Occasionally you get a problem that says real life quantity doubles in a fixed time frame. You're going to use this formula right here. A is still the initial amount. T is still time. K is a new one. K is how long it takes to double. In a similar way, we've got a formula if quantity is cut in half. This is also called half-life. But instead of 2 raised to the t over k, we have 1/2. As you can imagine, half-life, or cut in half, we use a half there. A is still initial amount. T over k. K is how long it takes to cut in half. What if the question says how long does it take to triple? Well, still have your initial quantity. Instead of 2 raised to the t over k, instead of 1/2, it triples. Well, triples is 3 t over k. Deer population doubles. Doubles, y equals a 2 raised to the t over k. And I need you to give me the a and the k. If there are 300 deer to begin with, that would be the initial amount. 300 to t. We need to figure out how long it takes to double. Population doubles every 9 years, so k is 9. Half-life. Half-life, a, initial amount, half t over k, how long it takes to be cut in half. All right, so we need the initial amount. If there are 200 grams of the element, that's what we started with. 1/2 t, and how long it takes to be cut in half, also called half-life. Well, I said the half-life is 12.2 years. And there's your final answer. And that is the last example for section 8.5. Let me know if you have questions in class.